In section 2.3, we're going to talk more about the definition of limits, and we'll get into the precise definition actually. And to do that, we're going to need to talk a little bit more about distance, and so I'm going to build a couple of concepts before we start talking about this definition of a limit. So the first thing I want to talk about is circles in the plane have a center point, and then they contain all of the stuff that is within a certain distance to that center point, right? So all of these points within a certain distance of the center is the circle's technically the outside. It's a disk in the plane. Okay. How does that work on a number line? On a number line, if I have a center point, we'll call it C, and I go some distance to the right and I go some distance to the left, I end up at C plus, I'm going to call it delta for a little distance, and C minus delta. Okay. And all of these points are the points that are within delta to C. And that's going to give us a little interval that's centered on C. Interval of, I'm going to still call it a radius. Radius delta centered on C. So even though I don't have a plane, I can still kind of think of it in the same way that I think of as a circle. And this interval centered on C sort of generalizes to 2 dimensions, 3 dimensions, you get spheres, and so on. Higher dimensions, you get higher dimensional circles, basically. And they're all called spheres. 4 sphere, 5 sphere, it's that sort of thing. But that's going to lead us into this limit definition. And I want to do a few things with intervals real close, real quick here. So if I have an interval, let's say I have the interval from 1 to 2. And I take any point in here. Let's say I take 1.8. Okay. And the question is, if this is C, how big can the radius be while I'm still inside the interval from 1 to 2? Right, well, if I make the radius 0.8, I would go to this end point, but 0.8 on this side would send me to 2.6, so that's no good. So I want to take the shorter of the two. If I take the shorter distance to the edge, and I call that delta, I can find this little sphere, this little circle on the number line where delta is 0.2, and so this will be at 1.6. And so if we center an interval of radius 0.2 on 1.8, the interval 1.8 minus 0.2 comma 1.8 plus 0.2 is inside the interval 1, 2. Right. So I found this point, or I was given this point, and I wanted to know sort of what size of an interval, what's the biggest centered interval on that point that will fit inside the interval 1, 2. Well, I go to the closest end point, and it gives me 0.2 to the right, so I go 0.2 to the left so that it's centered, and that interval will be centered on C inside the interval 1, 2 with radius 0.2. Right? Okay, that concept's going to help. So let me now write down this definition of derivative with deltas and epsilons and that sort of thing. And let me draw a picture first to kind of motivate this definition. So we're going to have a function, and we're going to try and find this limit. And if we're going to have a limit, I should put a hole in the function so that it doesn't really have to be there, but I'm going to keep a hole there just so we don't really care about what happens at that point specifically. Okay, and we're going to say that this limit is L. And what we want to do for this definition is, I want to say, as we get close here to C, all of the points on the function get close to L, right? As I'm traveling along the curve in any direction with my x values getting closer to C, my y values are getting closer to L, yeah? So as I'm moving horizontally, vertically I'm coming in close to L. So I'm going to get this sort of box here. And how I want to do this is, I'm going to tell you some tolerance on the outputs. I'm going to say I want to be within epsilon of L. That means I go to L minus epsilon and I go to L plus epsilon, right? There's L plus epsilon, there's L minus epsilon. This distance here and this distance here are epsilon. So if I want to be within epsilon of L, we're going to draw these horizontal lines, and then we're going to look at the function. The function crosses that horizontal line there and there, and that's going to give me some sort of interval around the point C, because L should be what we're getting close to as we get close to C. So there's going to be some distance here and some other distance here. And just like before, maybe this is at 2 and this is at 1 and C is at 1.8, right? These distances are fairly similar in this picture, but they don't have to be the same. And we want to know, how close to C do I need to be? Right? How close to C do I have to be so that all of the points in this vertical interval that we're going to draw on the graph are between L plus epsilon and L minus epsilon. So the first thing we get is we get these boundary points here, and then we choose the smaller one to be epsilon, right? We're gonna let this guy be epsilon, and we're gonna go epsilon this way as well. And so this will be at C plus epsilon, and this will be at C minus epsilon. And as long as we're in between, delta, these are deltas. And I missed one more. There's an epsilon, that should be a delta. We're going to put these to be the deltas, C minus delta. So this distance is delta, this distance is delta. And as long as we're delta close to C, we will be epsilon close to L. That's the goal. We need to figure out how small delta will have to be so that when we come up to this graph, all of the outputs that are within delta of C, all of the outputs that correspond to inputs that are within delta of C correspond to outputs that are within epsilon of L. Okay, let me write that out now. So we say that the limit as x approaches C of f of x equals L if given any, I'm going to call it a tolerance, any tolerance epsilon, which is bigger than 0 because it's going to be a distance, right? That's how far away from L we're going to be. If we're given any epsilon, any tolerance from L, we can find delta bigger than 0. We can find a little interval around C with radius delta such that if 0 is less than the absolute value of C minus x is less than delta. Okay. So this inequality says the distance between the point that I'm going to look at and C is less than delta, and C and x are not actually the same, right? With these limits, we don't want to look at the point, so this says don't look at the point, this 0 says don't look at the point, and this says we can get close enough such that if that happens, then the distance between L and f of x is less than epsilon. Okay, so we set up this epsilon tolerance. How close do we want the output to be to L? We can find a delta that, as long as my inputs are close enough together, like as long as the input that I'm going to use is close enough to the point that I'm approaching the limit at, that close enough is the delta. We can find that delta so the outputs are close enough together to L. Okay, so if that is the case, we say that the limit exists and it is L. Okay. Let's draw another picture. This picture sort of shows how this works positively, right? Like in the sense that this is the picture that we used to come up with the definition. Let's show something there. I don't have a limit and where this definition would break down because we don't have a limit, right? The definition should work only if the limit exists. So if the limit doesn't exist, this definition should break somewhere. So here's the picture of that. Let's say we have some function that looks like this, and I'm approaching C here, and I don't care where this point is, I'm just going to put it on there just so we have continuity, or a function that has a domain everywhere. Okay, so this is f, and no matter where I put L, if I would want to say, we want to say, suppose the limit of f of x as x approaches C equals L. No matter where I put L, let's put it up here first, L. Maybe we think it's approaching this guy, right? From the right, that's true. But now let's come up with a tolerance for epsilon. If I use a really big epsilon, then yeah, all of the C values within, say, this little delta range would lie in this rectangle that tells me that I've gone up epsilon and I've gone down epsilon, right, from L, and these guys, this bit of the function and this bit of the function are all inside this rectangle, so that would be good. But remember, the definition says for all epsilon. For all epsilon bigger than 0, we can find a delta. So I'm going to make epsilon small enough so that I can't find a delta. Let's make this guy our epsilon. So this was epsilon 1, which worked fine. Epsilon 2. So I'm going to go epsilon 2 up, epsilon 2 down. Okay, so now this part of the function lies outside of the rectangle, right? The vertical bounds on the rectangle, the top is here, the bottom is here. This bit will never be inside that rectangle, right? So no matter how close to C I make epsilon, or actually how far from C I make epsilon, right? This bit is never going to be inside the rectangle no matter how big I make delta or how small I make delta, right? This bit never gets inside there. Okay, so that's why this is a good definition for limits, because we can't do it when the limit doesn't exist, right? If there is a gap between where things approach from the left and where things approach from the right, if there's this gap here, we choose epsilon small enough that the deltas can't fix that gap. Can't make that gap go away when we're drawing our rectangles. Okay, so that's all the ideas and the concepts of this limit definition. I'm going to make another video and we're going to do some specific examples where we're going to come up with these epsilons and deltas, or we'll prove limits work in certain functions. Given an epsilon, we'll find deltas, or taking an arbitrary epsilon, we'll find a delta as a function of that epsilon that shows, yeah, this limit works and this is what the limit is. So we'll do that in the next video.